Hello, welcome students for the online lecture on fluid power systems. We are going to discuss module 2, that is pumps and actuators. In last class we have seen what is a positive displacement pump, what is the non-positive displacement pump, and we have seen the construction and working of gear pump. So today we will continue with the discussions of vane pumps. So first we will solve this problem which is on the gear pump. Determine the volumetric efficiency of a gear pump of external diameter and internal diameter of gears 75 mm and 50 mm respectively, and with the gear teeth 50 mm if the discharge is 30 liters per minute at 1800 rpm. So given things are: external diameter of the gear is 75 mm, internal diameter of the gear is 50 mm, width of the gear is 50 mm. Actual discharge is given 30 liters per minute. If you convert in meter cube per minute, it will become 0.03 meter cube per minute. So 30 liters per minute, if we divide by that by 1000, that is converted into meter cube per minute, because 1 meter cube is equal to 1000 liters. So we know that volumetric efficiency is equal to actual discharge divided by theoretical discharge. Actual discharge is given is 0.03 meter cube per minute, which is given. Q theoretical, to find the Q theoretical, we know that formula is Vd into N, Vd into W, where Vd is equal to volumetric displacement, which is given by pi by 4 d naught whole square minus d naught di whole square into W. So this is the discharge. Vd means it is discharge per revolution. If you multiply by N, you are going to get the theoretical discharge given. So Q theoretical is equal to Vd into N. So pi by 4, so Vd means it is pi by 4 d naught whole square minus di whole square into 50, that is width. Pi by 4, 75 whole square minus 50 whole square into 50. Convert that in mm into meter cube, meters. So you are going to get the Q theoretical equal to 0.110446 meter cube per minute. So therefore volumetric efficiency is equal to Q actual divided by Q theoretical. Q actual given is 0.03 and Q actual theoretical we have find it as 0.110446. So that will come 0.4532 multiplied by 100, it will become 54.32. So this is the efficiency, volumetric efficiency of the given pump. So we have discussed the positive displacement pump. So in all positive displacement pumps, so as the volume goes on increasing, the suction is going to take place, and as volume goes on decreasing, the discharge is going to take place. So as volume goes on increasing, vacuum is created and it will suck the oil inside it, and when the volume goes on decreasing, the oil is discharged. So in gear pump, as the gears are unmeshing, at that time volume increases, and at the inlet side unmeshing is going to happen and it is going to suck the oil inside it, and at the exit port the gears are meshing and volume is decreasing, and this is forcibly discharged out of the pump. The oil is forcibly discharged out of the pump. So volume going to increase, suction is going to take place. As volume goes on decreasing, delivery of the oil is going to take place. So this is going to happen in all types of positive displacement pump. So the vane pumps are also rotary pumps and operates on the principle of increasing and decreasing volume. Increase in volume of the cavity produces vacuum, which draws the fluid into the chamber and fill the space, and the decrease in the volume causes the fluid to be forced out of the chamber under pressure. In this case, the vanes are allowed to track along a ring, generally called cam ring. Types of vane pumps: fixed displacement unbalanced type, fixed displacement balanced type, variable displacement unbalanced type, variable displacement unbalanced balanced type. These are types of wind pumps. The important elements of wind pumps of unbalanced type are rotor with slots for wind. The rotor is going to be connected to the electric motor. So sliding vanes. So inside the slots, the sliding vanes are going to slide inside the slots which are on the rotor. Stationary circular cam. So the vanes are in contact with the circular cam housing. So below the above the cam ring there is a housing. So the rotor fuse axis is positioned eccentric. Here the rotor fuse axis is positioned eccentric to the circular cam. So circular cam and rotor, they are eccentric. The rotor fuse axis is positioned eccentric to the circular cam ring, rotates inside it. The vanes which are free to slide. The vanes which are free to slide inside the slots are provided in the rotor. Move downward due to centrifugal outwards. Move outwards due to centrifugal force. These vanes make contact with the inner surface of the cam ring and a positive seal takes place between the vanes and the cam. So when you start the electric motor, the rotor inside the housing will start to rotate, and due to the centrifugal force the vanes are coming out of the slots and they are in contact with the cam ring, and for half rotation of the vanes volume goes on increasing and suction is going to take place, and another half rotation of the vanes they are pushed inside the slots by the cam ring and volume goes on decreasing and discharge of the oil is going to take place. During one half of rotation of the rotor, the volume increases progressively between the rotor and the cam ring. This increases in volume causes reduction of pressure and in the suction and is the suction process, during which fluid flows into the housing through inlet port and fill the void. As the rotor revolves through the second half rotation, the surface of the cam ring pushes the vanes back into their slots and the volume becomes progressively smaller. This reduction in volume increases pressure and is the ejection process, during which the fluid flows out of the pump through the outlet port. The displacement of pump depends on width of the ring or the vanes or rotor and on the distance the vanes allowed to extend from rotor surface to the ring surface. So if you see the figure of the vane pump, so you can see the rotor, vanes, cam ring, outlet port, inlet port, and you can see the eccentricity between the cam ring and the rotor. So suction is connected, the inlet port is connected to the reservoir through filter and the outlet is connected to the system. So here for half rotation of the rotor, volume increases and suction is going to take place, and for next half rotation of the rotor, volume decreases and discharge is going to take place. So these are the disassembled parts of the vane pump. Rotor with radial slots. So here we can see the rotor with the slots with it. Radial slot, vane. So 5 slots are there, 5 vanes we can fit. So cam ring we have shown cross section of the cam ring. So volumetric displacement of the vane. So hatched area into width of the vane is nothing but the volume discharge per revolution. So outside cam ring diameter DC, dr means it is the rotor diameter, E is the eccentricity. So discharge depends also on the eccentricity. If eccentricity is 0, suction will not take place and discharge is not going to take place. So for vane pump there must be eccentricity to suction to take place and discharge to take place. Volumetric displacement, VD, is volume of the fluid pumped out of the or displaced per revolution of the rotor. With reference to the figure, the dimensions of the elements are DC, that is cam ring diameter, dr rotor diameter, E is eccentricity, width W is the width of the rotor. So pi by 4. So Vd is equal to maximum volumetric displacement. Vd means it is a volumetric displacement. Vd max means it is maximum volumetric displacement. So Vd is nothing but it is pi by 4 dc whole square minus dr whole square. Vd means it is pi by 4 dc whole square minus dr whole square into W. So pi by 4 dc whole square minus dr whole square can be written as dc minus dr plus dc plus dr. So pi by 2, so dc minus dr divided by 2, so 2 it is taken this side, so dc minus dr divided by 2 into dc plus dr divided by 1, that is equal to pi by 4. So dc minus dr divided by 2 means it is the maximum eccentricity we are going to get into dc plus dr. So volumetric displacement is equal to pi by 2 e into dc plus dr into w. So for maximum displacement or maximum discharge per revolution, so you must take e is equal to e max. When e becomes e max, at that time vd becomes v max. So vd is equal to pi by 2 e into dc plus dr into width of the rotor. So this is the volumetric displacement of the vane pump. Volumetric displacement of vane pump. Volumetric displacement Vd is the volume of fluid pumped or displaced per revolution of the rotor. Volumetric displacement means Vd, it is given by Vd, and it is the volume of fluid pumped out or displaced per revolution of the rotor. So a vane, next we will solve one problem. A vane has a pump has a rotor of diameter 50 mm, a camering of diameter 80 mm, and the vanes of width 40 mm. Compute the volumetric displacement and eccentricity is 10 mm if the eccentricity is 10 mm. So rotor diameter has given dr is equal to 50 mm, and camering diameter has given dc is equal to 80 mm, and width of the vane w is given 40 mm. So volumetric displacement Vd is equal to V theoretical is equal to pi by 2 dc plus dr into E into W. So Vd is equal to pi by 2, dc means it is 80, diameter of the cam, plus dr means it is 40 mm, convert that into meters. So E is given 10 mm, so 10 into 10 to the minus 3 into W. W means it is the width of the rotor, that is 40 mm into 10 to the minus 3, it is the meters. So volumetric displacement we are going to get 7.54 into 10 to the minus 3 meter cube per revolution. So this is the volume displaced per revolution. So per revolution, if you multiply 1000, you are going to get 0.0754 liters per revolution. If the RPM of the motor is given, if you multiply by the RPM of the motor, you are going to get liters per minute. So this is volumetric displacement, so which is equal to 0.0754 liters per revolution. This is per revolution of the rotor. Variable displacement pump. So here variable displacement means we can vary the discharge of the pump by varying the eccentricity. So we know that when E is equal to 0, suction is not going to take place and discharge also not going to take place. When E becomes equal to E maximum, so at that time discharge of the pump is maximum per revolution. By operating the screw, the geometrical position of camering with the center of the rotation of the motor can be varied. So a circle with the two arrowheads and the arrow mark shows the symbol of the variable displacement pump. So arrow mark indicates this is a variable displacement pump. So the above figure shows unbalanced vane pump. So here the rotor and the casing and the vanes, they are shown by the lines. So rotor, you can see inside that rotor the slots are there, and in slots the vanes are going to move, and motor is connected to the rotor is connected to the motor. When you start the motor, rotor is going to starts rotate. So when rotor is rotating, the vanes are coming out due to the centrifugal force and are in contact with the cam ring. So for first half rotation, the vanes are moving outside as the volume is going to increase and it is going to suck the oil inside it. And for next half rotation of the rotor, vanes are pushed inside the slots, and the volume is going to decrease, and the pressure of the fluid is going to increase. So in balanced vane type, there are two inlets and two inputs, two inlets and two outlets. So inlets are opposite to each other, and outlets are opposite to each other. So both are connected to the same pipe again. So suction is connected to the two inlets, and discharge is connected again to the same line. So why it is known as balanced vane pump means the forces which are acting at the inlet force and outlet force, they are equal and opposite, and forces are balanced and there is no stress in the shaft. That's why it is known as balanced vane pump. There are no stresses happening on the pump shaft, and without noise it is going to operate smoothly. It is going to operate as compared to unbalanced vane pump. So at the two inlets, you can see volume goes on at inlets are where we are going to take the inlet means where from where the volume goes on increasing. So next, where the volume goes on decreasing, where it decreases, at that point there are the outlets. So here, since it is since since the casing is elliptical type, and at the center there is a rotor is rotating. So here also for as the rotor rotates, the volume increases, and again volume is going to decrease. Two sides volume increases and two sides volume decreases. From where the volume decreases, there outlet is there, and where volume is going to increase to at 2 points, there are the inlets. A vane pump has a volume displacement of 82 centimeter cube. A vane pump has a volumetric displacement. So this is displacement per revolution, 82 centimeter cube per revolution. The diameter of the rotor is 50 mm, and depth of the cam ring is 75 mm. If the width of the vane or rotor is 40 mm, find the maximum eccentricity. So Vd is equal to 82 centimeter cube, that is 82 into 10 raised to minus 6 meter cube. Diameter of rotor is 50 into 10 raised to minus 3 meter cube. Diameter of cam ring given is this is equal to 75 mm, that is 75 into 10 raised to minus 3 meter cube. Width of the rotor is given 20 mm. So we are told to find the E max or E. For given discharge, you must find the E. So Vd is equal to pi by 2 E into W dc plus dr. This formula already we know. This is the volumetric displacement of the pump. So which is in meter cube per revolution. So meter cube Vd is given 82 into 10 raised to minus 6 pi by 2 E, we don't know E, into it is 40, convert into meter, and dc is equal to 75 and dr is 50 mm. 75 plus 50 into 10 converted into meters. So E we are going to get 10.44 mm. So for this much discharge, eccentricity is 10.44. And if you want to find the maximum eccentricity, for that you must dc minus dr, that is 75 minus 50 divided by 2 is nothing but it is the E max. E max will come 75 minus 50 by 2, 12.5 is the maximum eccentricity. If you put this E max in ED formula, ED is equal to pi by 2 E max. If you put that to E equal to E max, at that time you are going to get a maximum displacement of the pump. So for 10.44 eccentricity, discharge is 82.10, 82 into 10 to minus 6. But if the eccentricity is 12.5 ml, so discharge will be increased. This is Schwarz plate type axial pump. So piston pumps. We are going to discuss now piston pumps. So this will continue next class. Schwarz plate type axial pumps. Thank you.